welcome to It's Not Quantum Physics. Today we're going to be talking about oscillations and we're starting the simple harmonic motion topic. Okay, so we've got three different sort of objectives for this lesson. We need to be able to explain what's meant by one complete oscillation. We need to be able to define amplitude, frequency and period of simple harmonic motion and describe the phase difference between two oscillators that are out of step, and we'll get towards that towards the end of the lesson. So I would quite like you to now have a go at drawing a sketch to show how the position of the mass that you can see on the right hand side, it's a mass on a spring here, oscillating, and it's oscillating with simple harmonic motion, but we'll come back to that a little bit later on. But how does the position of the mass change with time? And I'd like you to have a go at drawing this graph before we actually go through it together. So your axes, actually I kind of gave you a bit of a red herring because the axis really needs to go in the center of the x-axis, because the y-axis, sorry, because we have got both a positive and negative direction on this spring. So let's consider the three situations. We've got the spring where it's there, got the spring where it's a bit lower, and we've got the spring where it's much lower. And the one in the center, which is where the mass will rest if we let it oscillate until it stops oscillating, until it's lost energy, will in fact be what we call the equilibrium point, but it's our zero is what we should consider that as. So that means we've displaced it. So let's start by having pulled it downwards. So we're going to have pulled it downwards. So we're starting in position C. Let's call this ABC. Start in position C. We have pulled it downwards. So we're going to start down here. Over a period of time, it will pass through zero, which is our equilibrium point. And then it will go to a positive at the same distance. Then it will come back through the equilibrium point, and it will go back down to the zero, or the lowest point again, back up through equilibrium, back up to the highest point. Now it's not straight lines, because you'll notice if you watch the animation very carefully, it's accelerating and decelerating at either end. It doesn't just stop, it slows, and then it speeds up again. So that means that we're going to end up with a curve. So hopefully you've ended up drawing yourself in this case, if I'm correct, a negative cosine curve. It doesn't matter whether you end up with a sine curve or a cosine curve. In this case, I've ended up starting at the negative point because I've pulled the mass downwards. If I had pushed the mass upwards, we'd have started up here. And if we'd have put the mass on and then started next equilibrium point and given a small displacement, we'd have started somewhere around here. So we are seeing that it's accelerating at one point. It's then decelerating to zero, turning point, back through, and then carrying on all the way across. So there we have a sketch to show displacement, and let's put some labels, displacement versus time for an object in simple harmonic motion. So we end up with something that looks like that, as you can see there. So we'll just go back to the PowerPoint for a second. Simple harmonic motion. What is it? What do we know, and how can we break down this statement? Because you need to know what objects are when they're in simple harmonic motion. So we've come across harmonies before. We've come across a harmonic, first harmonic, second harmonic. And as I put here, it's used as instruments were seen to vibrate when they're plucked. So as you found out last year, when you were doing your standing waves, you can have harmonics, which are different points when you end up with standing waves. So what else can we learn from this? Well, simple, because it's not physically complicated. It's complicated, don't get me wrong, this is physics, it is hard to understand. But simple in that we're going to end up some really nice simplistic equations to work with. And motion because it's not at rest and it's moving. So it's this idea of these harmonies, these harmonics that are simple because something is in motion. And let's have some examples of some simple harmonic motion situations. So I've got what have I got? I've got 4 for you to see, which are examples. And we'll start off with the simplest ones, the ones you're most likely to see. So here we've got a spring with a mass on the end. And if we displace that mass downwards, we apply a force to that mass and we move that spring, then the spring, as we've seen in the previous slide, will oscillate backwards, upwards and downwards, etc., etc. So that's our first one. We've also got pendulums. And pendulums, when they have been displaced, will oscillate, let's make it slightly longer, backwards and forwards through an equilibrium point in the center. So this will oscillate backwards and slow down, and then it will turn around and it will oscillate forwards, accelerating, and it will slow down, etc., etc. So we end up with exactly the same diagram. Now those are the 2 we see in the lab quite often, but what about 2 we might see in everyday life? In fact, I've got 3. We'll do one more. So you can have a person sat on a swing, and that swing will go backwards and it will go forwards. So again, we have got an oscillation of that person on the swing, because we have got, similar to a pendulum, we've got the same similar system. It's going to oscillate backwards and forwards and backwards and forwards, because we've got this situation where you're accelerating, you're no longer accelerating in the center, we'll come to that next lesson, and then you're decelerating and you're stopping and then accelerating backwards, and you keep doing that in a periodic fashion. So that's a nice straightforward one. We've got the situation where you might be driving your car and we might have a pothole, which you might find quite regularly on our roads these days. Now, inside of the car, we have got springs. And if you, let's try and draw this car relatively accurately. So if you hit that pothole, you will find that the car will oscillate upwards and downwards. And that car will oscillate upwards and downwards because it enters simple harmonic motion. So those springs there are allowing that car to oscillate upwards and downwards. Now, we know that it doesn't do that forever, otherwise a car might shake apart. Instead, something else happens, which we'll come to in a later lesson, which is called damping. And we can take it all the way to the sea. So here's the sea, and we've got a boat on the sea there. So this boat, let's give it a sail, is being hit by the waves at the side. So we've got waves coming in like this, passing through, and in which case this boat will oscillate from side to side, moving around the center point. And again, it's very much like a pendulum. The whole object oscillates, decelerates, then it accelerates, has no acceleration, decelerates, then it accelerates again, etc., etc., backwards and forwards, because the boat moves from side to side. So it enters simple harmonic motion. So some other examples for you we've now got on the slide. We've got a metronome. Let's make the PowerPoint full size. We've got a metronome here, which is obviously moving backwards and forwards. It's a bit like that ship that was moving backwards and forwards. We've got guitar strings, because remember, harmonies happen. You get your harmonics because those strings have been plucked, which means they move backwards and forwards along this axis here. So you end up getting that string moving along that axis, which is again simple harmonic motion, because it accelerates, then it has no acceleration, decelerates, then accelerates, etc., backwards and forwards. We've got people on swings, a dog, and we've got a person, and you've got something like a punching bag. If you punch it, it's going to swing like a pendulum. And these all follow simple harmonic motion. So this is a graph of simple harmonic motion, where you end up with the amplitude versus time giving you a sine or cosine curve, because of that idea that I've been mentioning already of acceleration and deceleration at those turning points. And we'll come across that more in the next lesson, where we actually analyze this graph to give us acceleration and deceleration graphs. So here we go. This is the really simplest statement. Simple harmonic motion refers to any body that oscillates. If it oscillates in a pattern, then you end up with simple harmonic motion. And there has to be no driving mechanism, so we're not forcing it to oscillate. In other words, it's oscillating on its own. And also zero frictional force. Otherwise, if we have friction, obviously the amplitude is going to change over time. And again, we'll come to that in a later lesson. Now, how do we relate that to circular motion, which is what we spent a lot of time looking at over the last few weeks? I've got a video to help us with that. And I'm going to start and stop this video because I'd like to explain it as we're going through.
Good morning. Circular motion, when viewed from the side, is simple harmonic motion.
What?
Flippin' physics. Circular motion, when viewed from the side, is simple harmonic motion. Let's take a look at this turntable of a record player.
Okay, so what we've got here, we've got that yellow pen cap that's on the record player. It's going round in a circle, which is meaning it's within circular motion. So remember that there would be a force acting towards the center, which is our centripetal force. So there's an acceleration causing that pen lid to keep moving round in a circle. And we're going to look at it from different perspectives to understand how circular motion relates to simple harmonic motion.
I have placed a yellow marker cap on it so we can observe the circular motion of the cap. Does everybody see that the cap is moving in circular motion?
Yeah. Yep. Yeah.
Okay, now let me add a side view of the turntable and yellow marker cap.
Okay, so looking at the side view now, you can see that as the cap is reaching the top, it's got a greater distance to go round the circle, which means it stays in that top section for longer than it does in the centre and the bottom. But as you watch that yellow cap move from the side view, it appears to follow the same circular motion that we've been talking about in our simple harmonic motion that we've been talking about in this session.
Do you see how the cap appears to move in simple harmonic motion?
Yeah. No.
Okay, so then I will add a vertical mass spring system moving in simple harmonic motion. Now do you see how the cap appears to move in simple harmonic motion?
So notice that the mass on the spring follows exactly the yellow cap because it is following that simple harmonic motion that we're learning about today.
Yeah. Sure. Yep.
In fact, we can also add a front view of the turntable and yellow marker cap. And we can also add a pendulum moving in simple harmonic motion. Do you now see how the cap, when viewed from the side, moves in simple harmonic motion, just like a mass spring system and a pendulum?
I saw it from the start.
Yeah. There's a lot going on in this.
Okay, sure. So there is a lot going on. So I will simplify it by removing everything but the turntable and yellow marker cap. Now I will add a dot that is motion tracked to the top of the cap.
So as we've seen so far, if we're in simple harmonic motion, we should have some kind of sine wave or cosine wave to see what's happening with regards to the displacement from the center. So let's see whether that happens.
And I will isolate the motion of the dot so it is only moving in the y direction. This dot is now moving just like the side view of the cap. In other words, this dot is moving in simple harmonic motion. And watch the path it creates if we look at where the dot is located as a function of time. Does anybody recognize the shape of that curve?
That is a sine curve.
Actually, I think it's a cosine curve. Actually, it could be either one. Sine and cosine are just shifted along the horizontal axis relative to one another. Right, Mr. P?
Yes, this could be a sine or a cosine curve. It just depends on where it starts along the horizontal axis. So remember, simple harmonic motion and circular motion are related because circular motion, when viewed from the side, is simple harmonic motion. Thank you very much for learning with me today. I enjoyed learning with you.
Okay, so what we were able to see there, as the gentleman said at the end, is this idea that circular motion and simple harmonic motion are very, well, in fact, the same when you view them from different axes. And this is really important when it comes to the equations we're going to be using for simple harmonic motion as we move forward. So let's go back to the PowerPoint. So we've got some definitions now. These are really, really important definitions, and these are the ones that you have to make sure you know, which relate to simple harmonic motion. So to start off with, displacement is the distance that an object has moved from its mean or rest position, or in fact what we've been calling the equilibrium position. It's how far the spring has moved upwards or downwards relative to that central point. Now, a maximum displacement in either direction is known as the amplitude. So if you go to the maximum positive displacement, i.e. the spring has gone to the point where it's compressing the most, then you have a maximum displacement, so you have an amplitude, or the opposite, the longest that the spring can get to would also be the amplitude in the opposite direction, and they're both measured relative to the equilibrium position. And remember, we've seen amplitudes when it comes to graphs before, because they are the top, the peak, to the center point and to the trough, so they are both the amplitude. The frequency is the number of oscillations per unit time at any point. So if I have a 20 Hertz frequency, that means I'm having 20 full oscillations in 1 second. Unit time here is seconds. So the time period is the time it takes for one complete pattern of oscillations to take place at any point. Here we can say that the time period is 1 over frequency, which we've learned previously, and that just means that 1 over 20 would be the time it takes for you to have one wave passing at a frequency of 20 Hertz. If I've got a frequency of 1 Hertz, then the time period for that wave to pass a given point in space would be 1 second, because I'm getting one wave per second. And the angular frequency, as we've learnt again in the previous topic, is defined as the number of radians you have, i.e. one whole cycle being 2 pi, divided by the time period for that, or 2 pi times by the frequency. So if we had a frequency of 20 Hertz, then my angular frequency would be 40 pi Hertz, because I would have 40 lots of pi per second. Radians per second, sorry, that it's moving in. Okay, so those are our really, really important definitions, and I would make sure you learn those, note them down and learn them as you're going. So let's just now talk a little bit about phase difference. Here we've got an example of how we can relate simple harmonic motion on the left to circular motion on the right. Now that red dot, I know it's moving very, very quickly, but that red dot, as it moves upwards and downwards on the simple harmonic motion graph, is moving upwards and downwards on the y-axis relative to the circle, which is your amplitude, your peak points, positive and negative. And what we've then got is we have got an angle, omega t, which is relating to where in that cycle, where in that single cycle of the wave you are reaching. So at 2 pi on the simple harmonic motion graph, we have in fact oscillated all the way around the circle on our circular motion graph. And this is why we can put 2 pi on the simple harmonic motion graph, because those two things are related. Now a phase difference would be two graphs like this, and you could draw the phasor, which is what we call the circle with this line on it. And the difference between two phasors gives you the phase difference. So if I had a second graph that was exactly the opposite, so mirrored, then we would see the, let's call it a green dot. The green dot would move in exactly the opposite way to the red dot, and we would find we are pi out of phase, because there would be a pi difference between every single point that it's happening at. So that's the idea of a phase difference. It's the difference in terms of angular frequency between two objects that are oscillating at the same frequency but have had their starting points shifted. And we're going to have a look at that in a little bit more depth now, looking at the visualizer. So let's go to that one. So here I've got 3 swings and a person who's timing them. The guy in the green jumper or t-shirt is moving backwards, which we're going to call a negative displacement. So he is going to start from a negative maximum displacement, which is the amplitude. And the guy in the red here is moving in the opposite direction, which we will call a positive displacement. And we'll say he's starting from a maximum positive amplitude. Now, as he is reached the maximum, he is going to stop. He is going to turn around and move back towards equilibrium, which is where this third swing is. It's sat at equilibrium. So he moves through 0. He will then move into the negative direction. He will stop. He will turn around and go back again. So we end up with this curve here. If we look at the gentleman in the green t-shirt, we will find that he is starting in the negative maximum displacement, and he's moving towards the 0, and then going to move positive, and then back to 0, and then negative, etc. So if we were to do two phasors of this, so that is our circles, then I would have a point here where that's my center. So that would be my first phasor. And taking the same point along, my circle's a bit too big, but never mind. Now if I overlay those two on top of each other, draw ourselves another circle, and we'll have the red direction in red from the center point, and we'll have the green direction, the green phasor in green. Then we can see that the angle between those two, so the phase difference, would in fact be pi, because it would be 2 pi divided by 2, which is pi. So we can see this would be out of phase by pi. Now, let's do this with some numbers, because we can actually make ourselves an equation to understand this. So we'll just get rid of the phasor diagrams. If this person is timing the red person, so we'll say the red, let's go with red. So man in the red, and it's going to be the time period of the man in the red. We will say he is starting at 0 seconds. So that's when we've taken our time period for, it's when we start our stop clock. And the time that the green person has reached the starting point of the red person, we're going to say is in fact 0.2 seconds. So it takes 0.2 seconds from to go to negative amplitude to positive amplitude. So it must mean it takes another 0.2 seconds to go back. So therefore my total time period is going to be 0.4 seconds. Now, the phase difference is going to be the change in time divided by the time period, because that's going to give me how much of a cycle I'm out by. So in this case, it's going to be 0.2 over 0.4, which is in fact 0.5. But that just tells me I'm 0.5 of a cycle out from each other. That's not my angular phase difference. So my angular phase difference is going to be 2 pi lots of my difference between them, because remember, one whole cycle is 2 pi angle, as you can see at the top over here. So let's do this calculation. I've got 2 pi lots of 0.2 all over 0.4, which is in fact pi. So I have a phase difference of pi radians between these two people on the swings. So they're out by 1 lot of pi, and that's the difference between them. Now it's going to be your turn to have a go at a couple of questions. We'll ignore the experiment. We would do that in the classroom. So we'll do that when we're back to school. But it says here we've got 2 questions, question 3 and question 4, both of which I would like you to have a go at now, and pause the YouTube video to attempt them, and then come back in a few moments once you've had a go, and we'll go through the answers together. Okay, so let's go through some of those answers. And let's just go for that one. Right. So question 3 asked us to an object is suspended from the lower end of a vertical spring is displaced downwards from equilibrium. So as always, let's draw ourselves a diagram. So it's on a vertical spring. Its object has been suspended and it has been displaced downwards, so that means we are going to pull it downwards so that it starts at a lower point. It takes 9.6 seconds to undergo 20 complete cycles of oscillation. So we can say T20, so that's 20 lots of T, is 9.6 seconds. So therefore T is going to be 9.6 divided by 20, which gives us an answer of 0.48 seconds. So the time period for one oscillation is 0.48 seconds. So first of all, we've done work out the time period, that's A. And B, the frequency of oscillations. Well, we know that frequency is equal to 1 over the time period, which means I've got 1 over 0.48, which is going to give me 2.1 hertz. So there's our answer for that one and our answer for that one. So question 3 is done. Let's go on to question 4. So in question 4, we've got two identical pendulums, X and Y. So they're, or pendulums, sorry, not springs, pendulums. Well, that will make a difference, but, so there's pendulum X, and each consists of a small metal sphere attached to a thread of a certain length. Each pendulum makes 20 complete cycles of oscillations in 16 seconds. So in other words, they must be the same length. There's X and Y. So T20 is going to be 16 seconds. So therefore, the time period is going to be 16 over 20, which is going to give us 0.8 seconds. That's always useful to have before we start. Okay, so A passes through the equilibrium 0.2 seconds after Y passes through equilibrium in the same direction. Now, direction matters because what that says is there is the equilibrium. In fact, that means that... So X passes through. Let's just change my diagram slightly because now I've been given more information. So there's X passing through in that direction, and here we're saying Y, which we'll draw in red, is over at this point here, but also going in the same direction. So the time period between the two, so delta T, is going to be 0.2 seconds. So we want to work out the phase difference. Now phi is usually the symbol we use for phase difference. And phase difference is 1 whole cycle, 2 pi, multiplied by the time difference between the two, divided by the total time period. So that's going to be 2 pi lots of 0.2 over 0.8, which is a quarter, so that is going to be pi by 2 radians. So that's that one. And then X reaches maximum displacement at the same time as Y reaches maximum displacement in the opposite direction. So what we're saying this time is, so here's our next answer, we're saying that X is over here, Y is over there, and that is the equilibrium point. Same time Y. So we know that it takes 0.2 seconds for it to go from there to there. It's going to take another 0.2 seconds to go from there to there. So that means between the two there must be 0.4. So your change in time this time is 0.4 seconds. So therefore now we have a phi equal to 2 pi multiplied by 0.4 over 0.8, which is a half. So that is just going to be pi radians. Oh, no S on radians, just rad. So pi rad. Okay, so hopefully we've managed to cover everything that was in our definition that we needed to in this lesson. We'll just go quickly back to it and make sure we've covered everything. So explain what is meant by one complete oscillation, define the amplitude, frequency and period, and describe the phase difference between two oscillators that are out of step. So we've managed to calculate those phase differences. We can calculate them now, we can describe them. We know what amplitude, frequency and period are, and we know what one complete oscillation is. It's from maximum amplitude through equilibrium to negative maximum amplitude, back through equilibrium to maximum amplitude in the positive direction. It's one whole cycle. Okay, thank you for watching It's Not Quantum Physics. If you've found this video useful, give it a thumbs up, and you can subscribe if you want to follow any other videos that we have in the future.